27 kilometers of twin-tube highway, 392 meters below the North Sea. The deepest subsea road tunnel ever attempted anywhere. The problem is not drilling. It is ventilating, draining, and fighting fire inside a mountain under an ocean. Stay to the end, and you'll see why Rogfast could end up being the easiest of Norway's projects for crossing its fjords. Norway is building something never done anywhere on Earth, a road tunnel driven through solid rock 392 meters below sea level. Rogfast under Fjord will become the world's longest and deepest subsea road tunnel. 27 kilometers of twin-tube highway linking Haugesund to Stavanger, with a Kvitsøy junction 266 meters down. Laybys come every 500 meters. Exits every 250. Original budget, 16.5 billion kroner, about $1.6 billion. Every tunnel starts with the same uncomfortable question. What exactly is the rock doing ahead of the face? And is there water in it? Probe drilling checks geology and groundwater before explosives go in. If water appears, crews drill a grout curtain around the perimeter and inject cement into cracks, repeating every 20 meters. Then blast holes are charged, the crew evacuates, and one round advances 5 meters. Shotcrete seals fresh rock. 3 to 6 meter bolts pin the mountain against itself. The rig sends real-time data to software that color codes stability ahead. The rock can still ruin a perfectly scheduled afternoon too. Here's something that surprises people who have never been near a tunnel blast. Surface slope cutting may use 100 grams of explosive per metra, while one underground round can take over 1,200 kilograms. At that point, road construction has a very loud opinion. On the 9.5 kilometer E134 project, driven from both ends, holes ran 5 to 6 meters deep across an 85 square meter tunnel face. Consumption reached 2 to 2.5 kilograms per cubic metra. After evacuation, ventilation cleared gases, mucking removed rock, and bore sensing sent geologists live data on water, clay, and weak zones ahead. Solback Tunnel shows how Norway builds long road tunnels. Apply the same drill and blast methods to twin 8-kilometer tubes beneath the seabed, and every surface problem becomes harder underground. Solback Tunnel used full-face excavation, conveyor belts for muck, rock bolts after every blast, water and frost membranes, reinforcing mesh, and final shotcrete. A slip-form paver laid the concrete road base. The bottleneck isn't blasting. It's keeping power, ventilation, and water removal ahead of the heading. Water removal is immediate, constant, and catastrophic if the pump stops. Norwegian tunnel work confirms the sump pump runs at the lowest heading. It misses one shift, and everyone remembers the sea outside. Rogfast confirmed this at scale. Site visitors found LHA-110 submersible pumps handling groundwater and construction water in a tunnel descending nearly 400 meters below sea level. Once the portal is established, the question becomes, how does anyone keep 27 kilometers online? Before you can understand what Rogfast is solving, you need to understand what it's replacing, and why that replacement took until now. E39 runs 1,100 kilometers through 6 counties, from Kristiansand to Trondheim. 7 ferries interrupted. Driving takes 21 hours. Parliament chose to remove the ferries, cut travel to 11 hours by 2050, and spend over $39 billion across the corridor. Rogfast is the first fixed link across Fjord. Most people miss a ferry and complain. Norway missed enough to redesign the coast. As the contractor put it, to Stavanger, drive there. But 27 kilometers of twin tunnel under a 392 meter deep fjord is different. The title, World's Deepest Subsea Road Tunnel, sounds like a marketing line. The engineering implications behind it are not. Rogfast drops 392 meters below sea level, where water pressure turns a leak into a structural event. Two separate tubes carry traffic in opposite directions. Cross passages every 250 meters mean any driver is within 125 meters of an exit into the parallel tube. The route links Haugesund and Stavanger, putting hospitals, airports, and industry within reach without ferries. At that depth, backup plans stop sounding fussy. Investigating rock ahead is not optional. It is how the heading survives down there. Keeping a tunnel online across kilometers of blind drilling requires visible precision. Laser guidance projects the theoretical excavation cross-section onto the rock face, so operators see the boundary while excavating. It reduces overbreak, concrete overage, and cost. A few millimeters today becomes an awkward meeting 20 kilometers later inside. The northern Fjords section is worth about 5 billion kroner, about $500 million, with over 250 dedicated staff. The joint venture brings mass displacement, excavation, and blasting expertise at scale. Rogfast spoil goes to land reclamation, including new commercial and residential areas on Norway's west coast, instead of becoming waste. On this project, even the muck somehow gets promoted on site. The discipline that moves rock from a heading to a destination is the same, whether it comes from a data center foundation or a subsea tunnel. In Undheim, 50 to 55 semi-trailers ran continuously, while every Monday the site manager, operations lead, and logistics coordinator chose which tip sites and fill areas received the next week's spoil. At peak, 80 workers operated on site. Rogfast faces the same logic. 5 meters of advance per blast across multiple faces creates enormous volume, and someone must know where every cubic meter goes before the next round fires. Otherwise, it is traffic with invoices. Here is the hidden problem. Not every explosive detonates. Misfires sit live in muck. Mechanical detection failed. Dogs trained from 8 weeks clear 20 centimeter layers. After all that engineering, the nose still won. On Kvitsøy Island, the project hits its most complex chapter, and the team on site is not shy about what they've accomplished. In the fresh-cut intake shaft, the manager says the underground roundabout, the spaghetti, is 100% excavated. Lanes, ramps, passages. Bridge structures are beginning. The leg toward Skanska has started. Geology passed through greenstone, green schist, phyllite, and black schist before improving into clean rock, better than predicted. Even the rock behaved, which is not normal policy. You take that news and keep moving. After excavation, the raw rock tunnel is not the finished product. A 90 km/h road needs layers. Cast-in-place lining bolts brackets into rock with 2-component epoxy, mounts PE foam with front and back plates, adds mesh, electrical conduit, and shotcrete until embedded spiner sensors confirm thickness. Precast lining builds foundations, anchors, brackets, hangs membrane behind concrete elements to drain water into side channels, then lifts wall and ceiling panels into place. Mixed systems use wall elements below and PE foam overhead. On Kvitsøy's steep ramp, water is not cosmetic. If it reaches the carriageway, the mountain has joined traffic management. The lining must solve it before drivers arrive. The numbers behind water and frost protection are not small. In the 9.4 kilometer E134 tunnel, crews drilled 90,000 bolt holes for 200,000 square meters of PE foam, 28 football fields. Water drains behind it. 8 centimeters of fire-resistant shotcrete protects it. Electrical work began autumn 2018. Opening came December 2019. Access behind the lining? None. Get it right. On the surface, above Norwegian road projects, the same rock logic applies. The 774 million kroner, 12.8 kilometer E39 Betna-Hestnes section uses blasting, 100% material reuse, electric crushing instead of diesel, wetland restoration, 5 bridges, 3 culverts, and a 90 km/h target. Rogfast keeps that speed under Fjord, just without daylight. Rogfast is the achievable E39 problem. Further north, Jordan is 4 kilometers wide and 450 meters deep, forcing floating foundation suspension bridges, 450 meter land towers, or submerged tubes 30 meters down. Tested in wave basins and wind tunnels, none exists at this scale. Norway calls that planning. Most countries call it a dare. And if Jordan is hard, Sognefjord keeps engineers awake at night. The Sognefjord is 3.7 kilometers wide and 1,300 meters deep, with no structure crossing it. 5 concepts were studied: a 700-meter suspension span, nearly 3 Golden Gate bridges, 450-meter towers, 150 meters above the Eiffel Tower, a record-scale floating bridge, and submerged tubes 20 meters down. All are technically feasible. None is routine. 1,300 meters deep. That is not a gap. That is an engineering argument. Whether it gets built is political. But here's what Rogfast proved. Norway will build what it decides to build, underground, under the sea, at any depth required. The Kvitsøy underground junction needs surface infrastructure above it, and that means reclaiming land from the sea. On Roadway, an 85-decare industrial area rises from reclaimed seabed. A 370-meter barrier temporarily connects Jartholmen to land, dropping Kvitsøy's advertised 365 islands to 364. Losing an island is awkward. Losing it to site logistics is almost impressive. Split barges fill progressively to KT-10 before hard fill begins, because the collapsing underwater edge can take machines, equipment, and people with it. 4-tone armor stones interlock randomly to absorb waves. Safety started with worst-case scenarios, then mitigation. Every Norwegian road tunnel follows the same geological protocol, because the geology doesn't care which project you're on. Sokna-Ørgenvika drove the 2.8-kilometer Alray tunnel and 3.7-kilometer Ørgenvika tunnel simultaneously from both ends, with shifts monitoring conditions continuously. After each blast, geologists mapped rock, fractures, weakness zones, and water. Inflows under 1 litre per minute used reinforced shotcrete. Heavier inflows required grouting. Wall elements were made on the coast, shipped to Drammen, then trucked to the mountain. Even the concrete had a commute. Opened the 27th of June 2014, after 3 years and 9 bridges, it cut 20 kilometers and saved nearly 20 minutes. In the tunnel face, geology changes every 5 meters, so support changes too. Bore logging watches water, fractures, and weakness zones, shifting from bolts to reinforced shotcrete or grouting. The rig is both drill and sensor. Probe, interpret, classify, respond, blast, reclassify. That loop repeats across Rogfast's 27 kilometers. The largest single mass movement along Lake Mjøsa since the last ice age is how Norwegian engineers described this project, and they meant it literally. The combined E6 Dovrebanen project moved about 5.2 million cubic meters of rock, 33 Oslo city halls by volume. Joining motorway expansion with double-track railway construction saved at least 400 million kroner because E6 surplus rock became railway embankment fill. At peak, 1,500 workers operated across the site while existing E6 traffic and Dovrebanen trains still passed through. Blast rounds shut down road and rail together. Commuters waited up to 30 minutes, and trains were suspended for a week during critical realignment. Nothing says modern transport like stopping 2 transport systems so you can build 2 better ones. The project included 7 tunnels, 3 twin-bore road tunnels, and 4 railway tunnels, including the 3.9-kilometer Ulven tunnel. There, a continuous waterproof membrane worked like an umbrella, with concrete cast outside it to keep the railway tunnel dry. At Rogfast, multiple headings, contractors, spoil routes, safety systems, survey teams, temporary power, ventilation, and surface logistics run at deeper scale. But the coordination philosophy is identical, only much wetter and darker underground. Norway's largest tunnel project by total length combines an E16 highway tunnel and a double-track railway tunnel between Arna and Stanghelle. And the breakthrough cost saving is the shared emergency escape system. A single rescue passage links both tunnels instead of building separate escape routes, cutting duplicated underground excavation. Road travel time falls from 30 to 20 minutes, while rail travel time drops from 28 to 14 minutes. Rogfast applies the same idea with cross passages every 250 meters. The geometry is straightforward. Executing it at Rogfast's depth is not. Building a ventilation shaft is not the same problem as building a tunnel, and the people who have done both will tell you the shaft is harder. At Arlinger, the Central Operations Zone sits 490 meters from the south portal and 742 meters from the north portal, combining an electrical gallery, ventilation gallery, cross passage, ventilation shaft, and connecting passage. The arch formwork carriage cannot enter whole. Narrow passages force crews to assemble it piece by piece inside the electrical gallery, a 3-week job. The machine that builds the tunnel first has to be built inside the tunnel. Civil engineering enjoys making furniture difficult. The vault is poured in 10 metre blocks, 180 cubic meters each, cured at 85% humidity to prevent cracking. Every joint gets a sealing strip and manual adhesive inspection. The ventilation gallery is larger again, 14 meters in diameter, about 3 meters wider than the electrical gallery, so extra formwork extensions are fabricated and mounted inside the gallery, at height, in tight quarters. At the north portal silo, every concrete batch is tested before pouring. Anything outside tolerance is reworked and retested. When the pour sequence starts, the gallery is not just getting a concrete skin. It is becoming the airway that will push fresh air hundreds of meters down to the driving face, one 300 cubic meter block at a time. For Rogfast, the same logic scales vertically. A shaft is not a hole for air, but a concrete, electrical, access, and inspection system stacked inside rock safely. The ventilation shaft at Arlinger goes 25 meters deep, and pouring concrete inside a vertical hole from above is not a standard truck job. A mobile platform descends on rails from fixed anchors, with workers entering through a dedicated lift gallery. Rebar is tied, formwork positioned, and each block rises 2.8 meters, taking about 30 cubic meters pumped through the shaft opening. After curing, the platform climbs, fresh air pipes extend, formwork resets, and the cycle repeats to full depth. Meanwhile, the on-site concrete plant near the north portal solves the supply problem. It mixes 9 cubic meters in 6 minutes and loads a transit mixer in the same window, using daily deliveries of cement, aggregate, sand, chemicals, and water. C35/45 concrete goes to the arch vault. Other specifications go to the floor slab. Every batch is classified to DIN standard before leaving the plant. If it fails, it is reworked, not wished better. At 300 cubic meters per arch block, outside ready mix would need a truck every 3 minutes. That is not logistics. That is asking traffic to become a religion. This is why big tunnel projects build concrete factories on site. They are not trying to look impressive. They are trying not to have an entire pour waiting for a truck stuck at a red light. Rogfast ventilation shafts face the same basic constraint, only deeper. The pour cannot pause because the access route is awkward, wet, or vertical. Concrete does not wait for better weather. The intermediate ceiling is something drivers barely notice, and engineers spend months building. At Arlinger, the Zwischendecke runs 1,020 meters through the tunnel, separating traffic below from the ventilation duct above. A rail-mounted transporter carries the formwork table to each position. The crane sets the table at the portal. The transporter hauls it inside, and 1 ceiling block is poured per day, 18 blocks in total. The rescue tunnel created its own problem. The final 2 vault blocks were too large for the rolling steel carriage, so crews built timber formwork by hand. Precision stayed at millimeter level, inside a tunnel, in limited light, under deadline. The escape cross passages were poured with the rolling arch carriage moved sideways into each passage, a relocation taking 7 hours every time. 7 hours just to move the tool. Then the actual work begins. For Rogfast, the equivalent challenge is structural separation in the ventilation hall. Supply, air, and exhaust air must run through the same underground system without mixing, using concrete dividing walls built inside a rock chamber 200 meters underground. That is the unglamorous heart of ventilation engineering. Not more air, but separated air, moving exactly where the fire model expects. Getting asphalt into a completed tunnel and laying it correctly is harder than it looks, because the sequence matters before the surface ever appears. First comes gefallenbed, the leveling concrete that creates the drainage gradient. Then recycled excavation material forms the subbase, compacted and density checked with a Troxler probe after each pass. Only then does the asphalt sequence begin. 14 centimeters of base course, 8 centimeters of binder course, and a 4 centimeter split mastic surface. Arlinger placed about 965 tons of surface mix in the main tube in one session. Aggregate chips were spread onto the warm asphalt and rolled in for friction, the same motorway technique brought underground. The vault arch was then painted white to 3 meters high, so headlights reflect toward the driver instead of vanishing into dark concrete. A white wall sounds decorative until you remember people will drive here tired, fast, and underground. When Rogfast is paved, the same sequence runs under the North Sea. Drainage gradient, sub-base, asphalt courses, friction surface, visibility treatment. The asphalt is ordinary road asphalt. The location is 392 meters below sea level. At depth, bad drainage is not a puddle. It is a maintenance issue with nowhere convenient to go. This is the part of tunnel construction that quietly determines whether everything else will last. The moment an excavated tube becomes a controlled environment. Arlinger required 240 kilometers of cable, 1.4-ton jet fans, 20 smoke dampers, and 2 axial fans, 2.8 meters wide, 6.8 tons each, 400 kilowatts, moving 123 cubic meters per second. Comforting, until you remember the fan is bigger than a car and lives above a road. Then come emergency phones, cameras, speakers, sensors, 950 photovoltaic modules, fire simulation, and full rescue drills. That is when a tunnel becomes infrastructure. Before any tunnel goes under a fjord, someone has to know what the rock looks like down there. Offshore seismic surveying fires compressed air into water. Sound reflects from rock boundaries back to towed sensors, mapping geology by time delay. It finds fault zones, clay, and fractures. Without it, you are guessing in the dark, literally. Norway drills through rock. Denmark sinks pre-built concrete tubes. The Fehmarnbelt concept shows a different undersea answer. Lighting zones shift color along 18 kilometers to reduce monotony, while natural light portals ease eyes from daylight into artificial light. Tunnel interiors are not decoration. In kilometer 15, driver attention is an engineering system. Here's how you build an 18-kilometer tunnel under the sea without drilling a meter of rock. Manufacture it on land and sink it. Fehmarnbelt uses 89 immersed elements, each standard unit 217 meters long, over 73,000 tons, with 2 road tubes, 2 rail tubes, and a service tube. A 12-meter deep trench removes 15 million cubic meters of seabed, mostly reused for reclamation. Elements are floated out, sunk, and joined with hydraulic arms and rubber seals to 12mm precision. Rogfast cannot do this. Fjord reaches 500 meters. Drill and blast was the only viable approach. The German end of Fehmarnbelt shows a Rogfast lesson. If roads cannot carry materials efficiently, use water. Puttgarden gets weekly supply ships, pours the portal floor wall's roof, and starts 12 meters below sea level. Weather complains. The 2029 deadline does not. A 73,000-ton Fehmarnbelt element floats with empty ballast tanks, then receives 4,500 tons of ballast concrete in 4 zones while a compactor works inside it. Weight balance is critical. A listing element cannot be positioned. Sensors, guide beams, hydraulic arms, and rubber seals align the joint. 73,000 tons, and the error budget is measured in centimetries. That is ridiculous in the best possible way. Rogfast used explosives. Fehmarnbelt floats concrete. Both end as roads under the sea. Break the rock. The next hidden problem is knowing the shape of what you just blasted out. A tablet links to an AR headset. Engineers scan the blasted face, capture overbreak in seconds, then generate the next blast pattern. Drill points project onto bare rock. 5 minutes, no chalk lines. Air in, exhaust out. Somebody has to engineer both directions. A different family of underground pipework rides along the tunnel crown. Flexible duct sewn at the seams with industrial thread, reinforced with steel wire spirals, joined by high-frequency welding, hung from a messenger cable that carries the load. Smoke kills before fire does. Fans in road tunnels push exhaust on normal days, then pull smoke out on the worst day of the year. The tunnel may be ventilated, but the surrounding rock still needs protection. Finishing is what makes a tunnel last. Without it, the rock is just a wet hole. Rogfast runs 292 meters under the seabed. Crews outfitted 2 parallel tubes ahead of full blast completion. Cut a hole through a mountain, and the cavity won't hold itself open. Something has to brace the rock against gravity for 50 years. Drill and blast remains the older method, used for runs up to 3 kilometers. Tunnel boring machines work the other way. Full-face cutters up to 15 meters across, mounted on rigs that stretch 250 meters long. They eat through any geology and haul out the raw muck. The Austrian method, ATM, engineers the wall to use the rock's own load-bearing strength. Wall's done, now the floor. A feeder keeps the paver fed without stopping. 3 laser sensors smooth the asphalt into a mat. The surface is finished. The systems beneath it are still dark. The lights come on. The cameras are not for the tourists. Inside the road traffic control center, an operator sees a car stop on the camera feed. A red icon flags the position. He checks the image, finds the vehicle in an emergency lay-by, lets traffic keep moving. No closure needed. Watching traffic is half. The structure itself needs watching. Engineers anchor wireless sensor boxes to the wall, run cables, mount antennas, configure from a phone. Strain and movement broadcast back in real time. Sensors monitor, but somebody still has to walk in with a flashlight. Crews close tunnels at night to test fire equipment, open SOS phones, scan rock joints, clean camera lenses, vacuum sludge from drains, calibrate exhaust sensors, run the big ventilation fans. Every single job has to fit before sunrise. Before any tunnel goes live, somebody plans a day where everything goes wrong on purpose. A bus collides with cars deep in the tube. Smoke fills the gallery. Fire crews, police, medics, and a rescue helicopter arrive in minutes. Hydraulic cutters open jammed doors. Then the tunnel can finally open. A tunnel is not just a hole through a mountain. Every cabinet, sensor, camera, and exit door exists because engineers design the space around one question: what happens when everything goes wrong underground? That question drives a nationwide upgrade program touching 200 Norwegian tunnels because old safety standards no longer cut it. Retrofitting one tunnel means replacing lights, pulling kilometers of cable, adding SOS cabinets, emergency phones, signs, and safer control systems at regulated intervals. Night closures, rerouted traffic, and fast crews are expensive every scheduled night. A tunnel fire is more expensive. That is the meeting nobody wants twice. All that hardware feeds into one place. Traffic control centers monitor cameras, ventilation, and incident alarms around the clock. When a tunnel sensor trips, operators see it before drivers fully understand the problem. Here's a maintenance problem most drivers never consider. Tunnel exhaust, coats, surfaces, camera lenses, SOS signs, emergency doors, lights, and reflectors. Dry ice blasting removes that buildup without water or chemicals, so crews can clean safety equipment overnight. A camera covered in diesel film is not a camera. It is expensive decoration. In a long tunnel, maintenance is not housekeeping. It is the safety system staying awake properly between emergencies, every single night shift underground. Industrial tunnel washing keeps lane markings visible, reflectors working, and drains clear. Inside a sealed tube, visibility is not comfort. If drivers cannot see the exit might as well be decorative. The tunnel is only half the project. What connects it to the surface is what makes it useful. E39 Lunzit shell set shows fresh cuts, interchanges, and asphalt threading new infrastructure into the landscape for local traffic. Without that, a portal is just an expensive hole with excellent lighting after opening day. Most people assume excavated rock is a disposal problem. At Rogfast, it became a construction supply chain. Drill and Blast produces millions of cubic meters of raw rock, boulders, angular fragments, gravel, and fines. None of it automatically usable for road base, bridge fill, concrete aggregate, or marine reclamation. A crushing plant turns that mess into graded material. Jaw crushers handle the largest feed first, using a fixed jaw and moving jaw to fracture rock by compression. Cone crushers reduce the fragments further. Screening decks separate the output by particle size, coarse fractions for subbase and marine fill, medium grades for concrete batching, and fine material for sand and finishing layers. The bottleneck is the jaw crusher. Feed it oversized or poorly fragmented rock, and every downstream stage slows. That means the crushing chain actually begins back at the blast design, where drilling pattern and explosive loading decide how cooperative the muck will be. Even the rubble has to arrive in the right mood. Processed Rogfast rock supplied portal roads, access roads, shoreline platforms, and fill. Material that looked like a problem became the easiest building supply on site. On this project, even the muck got promoted into useful infrastructure too. Fixed crushing plants work when material comes to them. Mobile units solve the opposite problem. A tracked jaw crusher drives onto site, sets up quickly, and turns rock, concrete, or rubble into aggregate. For multi-phase tunnel work, mobile crushing keeps fill moving without making every load visit a distant plant. Connecting a portal to the road network is a concrete sequencing problem. A grade-separated interchange needs formwork, rebar, and a continuous pour that avoids cold joints before traffic ever reaches the open tunnel. Once the structure is solid, the road surface matters too. Green asphalt uses bio-based binders, recycled pavement, and lower temperature production. The road looks normal. The carbon bill underneath does not change at all. Laying asphalt is dangerous, and not mainly because of the machinery. Norwegian road workers reported 2 hazardous incidents per day from drivers ignoring closures and flaggers. Portal roads still need paving under live traffic, meaning the hardest variable on site may be the driver approaching too fast today again. Rogfast won't just replace a ferry. It will remove a variable: weather, schedule, queues, the whole negotiation between a driver and the sea, and replaces it with a fixed connection that runs at any hour, in any condition, without stopping. At 26.7 kilometers beneath the Boknafjord, it will become the longest and deepest undersea road tunnel ever built. That record matters less than what it represents: a decision to solve a geography problem permanently instead of managing it indefinitely. Does a tunnel optimized for today's traffic still make sense in 50 years? Does the cost justify the benefit at this scale? Rogfast is built on a simple idea. If the route matters enough, build it once and make the sea irrelevant for every future driver. What do you think? Is infrastructure expected to serve for decades worth the price? Tell us in the comments. Thanks for watching. The engineering stays interesting because the problems keep getting harder. Subscribe to keep the next one coming, and take care.